The purpose of this lab, the black hole lab, was to use the observations of a star's mass and motion to find the unknown mass of the black hole that the star is orbiting. In order to do this, I identified different interactions that make up the net force on the system, and used those interactions to solve for the unknown mass of the black hole, which I found to be 2.55 times 10 to the 31st kilograms. To begin, I used the given data of the mass of the system, which in this case is the visible star, as well as the x and y positions of the star at intervals of 1 Earth day, or 86,400 seconds, to solve for the net force on the system. This is under the assumption that the net force is due to only a single force from an uncertain agent interacting gravitationally with the visible star. The unknown agent is located at the origin of the coordinate system. Newton's law of gravitation can be used to describe the interaction between the star and the unseen object. Newton's law of gravitation can be used to describe the interaction between the star and the unseen object. It is calculated by g, a constant with a value of 6.67 times 10 to the negative 11th, multiplied by the product of the masses of each object and divided by the square of the distance between them. This law states that there is a force of attraction between any two masses in the universe. Plugging in the results from the motion analysis, the mass of the unseen object, the black hole, can be solved for. The momentum principle is also important, which in its basic form is dp dt equals F net. In other words, the change in momentum is equal to the net force acting on the object, multiplied by the duration of the force. Certain information was provided to plug into the code for the computational model, such as the mass of the star, which in my case was 4.0652 e to the 27th kilograms, as well as the time step of 86,400 seconds, and the position of the black hole, which was -3 times 10 to the 10th, -4 times 10 to the 10th, 0 meters. These values were updated in the given code, and then the data file which I downloaded was read in using this command right here. Now, the beginning of the code involves a while loop whose job is to calculate the velocity of the star during its orbit around the black hole. Following this, the second loop establishes several quantities of motion as it relates to changes in momentum and the net force. The initial and final momentum is simply calculated by multiplying the star mass and the calculated velocities, as seen here. The change in velocity, dp dt, is equal to the change in momentum over the change in time, as seen here. The net force was changed so that it would equal dp dt, which is according to the momentum principle. dp dt is just equal to the parallel component of dp dt plus the perpendicular component. When I run the code, the different arrows represent different aspects of the net force acting on the system. In the model, the yellow arrow is the total net force, while the blue arrow is the perpendicular net force, and the black arrow is the parallel net force component. The size of the arrow is larger when the star is near the black hole and smaller when it is farther away from the black hole. This was seen as it was very large when it was near the black hole at this point, and much smaller here. This is because the net force is inversely proportional to the distance between the black hole and the star. So I rearranged this equation right here into this format to solve for the mass, and the mass of the black hole was printed as 2.55 times 10 to the 31st. In order to determine if the calculation was accurate, I did the calculations by hand using the net force on the system and verified the value of the black hole mass. The parameters used to get the net force were the third position points in order to have two separate velocities calculated. So you can see the calculation that I did right here, and this differed slightly from the value that I got in the model. The computational model was 2.559, and the calculation I got doing it by hand was 2.495 e to the 31st. But these values are very similar, and they're within 3% of each other. I took that to reason that my model was fairly accurate in predicting the mass of the black hole. Let's answer some analysis questions. What does it mean? You can see from the momentum principle, F net equals dp dt, as shown here, and the F net parallel is equal to dp dt parallel, as well as dp dt perpendicular is equal to the F net perpendicular. So how do they differ? The main difference is found in how each component is calculated. F net in this case would be simply found by using the universal gravitational force equation. dp dt would be found using the equation shown in the code that uses differences in momentum over differences in time, as you can see here. So the main difference is that the net force is found by adding all the forces on the object, but dp dt is found by observing the motion, the actual motion of the star. What if? Imagine the black hole whose mass was removed and a different black hole is replaced. Would you be able to find a new value for the mass? You would not be able to find a new value for the mass because the motion of the star is unchanged and the data points given in the file are still the same. There is no alternative information given that would affect the mass of the black hole, and this is because the net force is calculated based on positions, velocities, and momentums of the system. Because of this, I would say that no difference would be able to be found and no new mass would be able to be calculated. Thanks for watching.